We've already discussed many operations over lists, like map, filter, for each. In this lecture, I want to talk about another category of operation over list, which is called a reduction or a fold. These have become famous because of map-reduce frameworks, such as MapReduce or Hadoop, in which a canonical sort of problem might be to count the appearance of each word in a set of documents. The problem is divided into three phases. In the first phase, the programmer provides a mapping function, which takes the contents and looks at those contents for all of the words that they contain, and then simply emits a bunch of categorized data. So here I'm categorizing the count of a word by the word itself. In the second phase, computation is divided among all the categories that were discovered, in this case all of the words. And then in the third phase, a reduction is called. For each word, I get a list of all of the partial counts. In this case, they would all initially be 1. And then I am going, in this case, to sum over all of those partial counts. I'm going to take all the partial counts and add them up. It's written in terms of partial counts here because the reduction may be divided into multiple phases. It may not all happen in one single phase. Google actually got a patent for MapReduce and its parallel execution. And indeed, parallel execution is the main appeal of these frameworks. We can perform work over massive amounts of data relatively quickly. But it might surprise you that you could get a patent for such a simple idea. And the idea of reductions and mapping have been around for a very long time. In this case, the summing operation is expressed in an imperative style, but as we've already seen, we can express these kind of sums also in a functional style. Let's look at one way of doing that. This is a sum function where I take a list and the initial value. I'll call it 0. I'm using something here called a default parameter in Scala. If the caller of this function only provides one parameter, Scala fills in the value of the second parameter to be 0. As usual on a function over lists, the function proceeds by matching on the list and doing a case analysis. In the case of nil, I simply can return the 0 or the initial value. And in the case of a cons, I'm going to perform the sum recursively, where here I've added in the head element into the 0. So this 0 is going to be an accumulator parameter. It will accumulate the value going forward. So here's an example list, 11, 21, 31. And when I call sum on that, Scala will fill in the default argument for z. So we'll start our accumulator initially at 0. And since we see a console up front, we'll perform the sum recursively. So note we'll recur on the sum with the tail, that's 21, 31, nil. And we'll take the 0 element that was passed in, the accumulator, and add the head. So we'll end up with 11 here. We then proceed with a case analysis on the tail list here, which still has a console. And so we'll take off 21 and add it into 11, giving us 32. We'll then take 31 and 32, add them in together to get 63. And what this function does in the base case is simply return the accumulated value. So when I finish here, I'll simply return 63. Note the order in which the additions happened. First, we added 0 to 11, then 21, then 31. We had an intermediate value of 32. This style of recursive computation may be less familiar to you because we're performing all of the computation here going forward. The more familiar style for you may be doing computation going backwards. And if we do that for a sum function, it looks like this. In this case, I've simply reversed the order of the addition and the recursive call. In the forward version, we perform the addition before the recursive call. In the backward version, we perform the recursive call before we perform the addition. How does this backwards recursion work? Well, again, starting off with the initial list, we have a case analysis which gives us this body here. So we'll end up with 11 plus the sum of the recursive call. That then does another case analysis, and again we'll end up with 21 plus the sum, we'll end up with 31 plus the sum, and only when we hit the base case do we actually return the 0. Once all of the recursive calls have unfolded, at that point we can start doing additions going backwards. So here we'll add 31 and 0. We'll then take the result of that and add 21 and 31. Note that we have an intermediate value here of 52, which we then add into 11 to get 63. So note that the computation here of the sum is actually happening in the reverse order. This is not a problem since addition is associative, and 0 is 0 on both the left and right. So note that the position of the 0 also moves. So when we do computation going forward, we initialize our variable to 0 and then add in as we go forward. If you notice, this is exactly what a loop would do. This is what the way loops compute going forward. Instead, in recursive calls, it's quite common to also do computation going backwards. And here I am computing the sum as I return from my recursive calls. So we have a different order of the operations. We have different intermediate values. This sum function is doing something specific on the list. It's got a specific notion of 0, and it has a specific notion of sum. So we can generalize this by parameterizing out the sum operation. I've already parameterized out the 0, so in fact, let's not call it 0, we'll just call it the accumulator parameter. So we've already factored out that accumulator parameter, but let's factor out this addition. So instead of doing addition here, I'll do an arbitrary operation. And obviously that operation needs to be provided as a parameter. I can then perform the sum simply by providing the sum operation to this higher order function. Fold left is the name of it. And how does this function compute? Well, it computes exactly the way that our forward sum computed. We're folding from the left. We first work on the first element added in, then the second element, then the third. That's how we fold from the left. Of course, once I've abstracted out the operation, I can perform different operations. So let's suppose instead of taking a list of integers into integers, let's suppose I wanted to actually print out a string of all of the integers in this list represented in hexadecimal form. I can do that by converting the output to a string. What I need in this case is a function that takes each integer and turns that integer into a string. That's what I have here. But in this case, I don't want to just convert a single integer to a string. I want to convert the entire list of integers to a string. So what I'm going to do here is use string concatenation to add a new integer format into an existing or accumulated string. So we'll accumulate this string going forward. I'll start with the empty string. Then we'll add in the string corresponding to 11. That's 0B0. Then we'll get 21. Then we'll get 31. And we end up with the resulting string here. Of course, I can also do operations over different kinds of lists. They don't have to be just a list of integers. So suppose I do an operation over a list of lists. And in this case, what I'm going to get out is a simple number, which is going to be the accumulated length, or the sum of the lengths. So in this case, the function I want is going to take a accumulated parameter and add that to the length of the second parameter. So here is a function which takes the accumulator and adds it to the length of the second parameter. And this will work here by running through the list and first looking at the length of this list, which is 3, then this list, which is 0, then this list, which is 2. So as we sum those things in, we end up with the result 5. This notion of fold is very general, and obviously we can abstract not only over the type of operation we're performing, but also the type of the list. And this is what the general form of fold looks like. We have two types. There's the type of the accumulator, or the zero, or the result. You can think of it in all these different ways. And the accumulated value is going to be combined with a new value at each step to produce a new accumulated value. And in the end, we'll return that accumulated value. We have the initial value provided, and then a list to operate over. And the function proceeds as we specified. So going forward, we first apply the 0 to the first element. In this case, I chose something different from the empty string. I chose bang. So now you can see a bang will be prepended here on the string before we look at the first element. Then we'll look at the second element, and note that that prior string then is going to be combined with the format. So here, instead of writing this using the underscore format, I'm using the lambda format. We have the 0 being passed in, which is a string. We have the particular element of the list, which is an integer, and we're combining those using string concatenation. That's folding from the left. Of course, if I can fold from the left, I can fold forwards. So this is going forwards through the list from left to right. If I can do it that way, I can also do it the other way. What is it going to look like? Well, all I need to do is swap the order of the recursive call and the operator. So swap the order of the recursive call and the operator. What is that going to look like? We have fold right. Fold right here performs the recursive call first before calling the operator f. So again, fold left, operate, then recur. Fold right is recur, and then operate. And what's going to happen here is that I'm going to go all the way down to the end of my list doing recursive calls till I hit the very end. And at that point, I'll first do the combining operation. Note that in fold right, the combining operation, as you might expect, is reversed in order. So when I was folding from the left, I had a string on the left. Whereas when I'm folding from the right, I'll get the string from the right. So the string coming from the right, and I will add it on the right. That's the other way from folding from the left, where the string is coming on the left, and we add it in on the left. And you'll see here that the 0, the bang, which I initialize with, shows up on the left in fold left, and it shows up on the right in fold right. And that makes sense because I go all the way to the end of the list, and then I put the 0 and then start coming back. So that's fold left and fold right. Fold left is a tail recursive function. What that means is that the recursive call is the last thing before we return. Fold right is recursive into an argument. What does that mean? It means that the recursive call is an argument of another function. So you can see here my operator expects as one of its parameters the result of a recursive call. So tail recursive means the recursion's the last thing we do. Recursive into an argument means that after that recursion, we'll take the value of the result and then perform some operator on it. So the order here, again, is just reversed. In fold left, we apply F to the head and the accumulated result, and then recur on the tail. Fold right, first we recur on the tail, then we apply F to the head and the result of the recursive call. The base case here in fold left is used on the first element. The base case in fold right is used with the last element. Scala has folds built in, and they are curried. So this is the way we write fold left in Scala. This is the way we write fold left in our own sort of list notation. So we wrote fold left taking a triple. In Scala, actually, fold left is a method of the list class that has 2 curried parameters in this form. Scala also has operators corresponding to fold left and fold right. These aren't amazingly popular. In fact, I just noticed they're getting deprecated in Scala. Nonetheless, they're kind of interesting to look at and why they chose this particular notation for them. So this is fold left and this is fold right. And let's just look the functions up here. Here's fold left and fold right. I'll just do this on a symbolic list, ABC. And I want to show you what fold left does on this symbolic list and what fold right does on this symbolic list. Fold left is going to perform the operation F first on the 0 element and the first element of the list. So that's F of Z, A. The result of that is then passed to the recursive call on B. And so the result of that is the new accumulated value for B. The result of that then is the new accumulated value for C. So if you think about the expression here and how this evolves, well, we have F first applied to Z and A. The result of that is then applied to B, and the result of that is then applied to C. Fold right works differently. In fold right, I first am going to go all the way down to the end of the list. Then I apply my operator to the last element, C, and the 0, Z. Then the result of that call is given to B. The result of that call given to A. And if you think about what that's doing as a syntax tree, well, the first operation is C applied to Z. The second one is B and F. And the third and final one is A applied to that result. So we're going in different orders through these 3 elements. And the notation here chosen in Scala is sort of indicative of that. So here we're going on the left branch. The 0 is down at the bottom of the left as we branch back up. And here the 0 is down at the bottom on the right. As we branch back up, you can see it. Recall that in Scala, operators are reversed in their binary form if they end in a colon. So this is indicating a method of the list class. Likewise, this one is also a method of the list class, despite the fact that they're reversed in this way. Folds are very, very powerful, and you can express pretty much anything as a fold. You can express the sum operation, the product, logical AND of a whole bunch of things, logical OR of a whole bunch of things. You can express the append function by folding using cons. You can express the flatten function by folding using append. You can express the length function by folding and just accumulating 1 for each result that you see. You can express the reverse operation by folding using a post-pending append operation. You can express map and filter with folds as well. There's lots and lots of things we can do. Folds are quite powerful, and this is a nice page that gives you sort of an intuitive feel for various things that fold left in particular can do. But there's also some interesting mathematical work on fold left and fold right, and it turns out that there's a certain formal way in which you can express that folds are universal. So if you're interested in this more academic approach, check out that paper linked here.